Hello, I welcome you all in this course on steam and gas power systems, and today we will discuss impulse reaction steam turbine performance, and we will focus on mainly Parsons turbine because it is mainly it is used as a impulse reaction turbine. So, gross stage efficiency of Parsons turbine, diagram efficiency of Parsons turbine we will drive, and then we will do one worked example. Now, in a Parsons turbine, there is a pressure drop in the nozzles and the stage as well. That is why there is an increase in specific volume in subsequent stages. This also helps us in right. So, there is an increase in specific volume in subsequent stages. Delta H is also not constant in all the stages, mainly it keeps on increasing in subsequent stages of Parsons turbine. The value of rho, it also does not remain constant for all the stages, and it also varies from stage to stage. That comes into the picture when we design a Parsons turbine. And mean diameter of fixed and the moving blades is same for a particular stage, that remains constant for a particular stage. So, in a Parsons turbine, I already explained that nozzle inlet angle is equal to blade outlet angle, and nozzle outlet angle is equal to blade inlet angle. Outlet relative velocity is equal to absolute velocity at inlet, and relative velocity at inlet is equal to absolute velocity at outlet. So, these are the conditions for Parsons reaction turbine. We will start with gain in the kinetic energy in moving blades. In moving blades, the gain in the kinetic energy is VR2 square minus K square VR. So, instead of K square we will take phi, carry over coefficient phi VR1 square by 2. So, increase this enthalpy in blades, change in enthalpy in blades is going to be VR2, we can always write V1 square minus 5 VR1 square by 2 efficiency of the nozzle or efficiency of the blade, both are same. Now, here VR1 square. Now, let us draw the velocity diagram also, because frequently we will have to give the reference of velocities. Now, in Parsons turbine it is similar. So, this is blade inlet angle, blade outlet angle, nozzle inlet angle, nozzle outlet angle, right. This is V1, VR1, VR2, V2, and this is U. Now, here VR1 square. So, VR1 square, again it is V1 square plus U square, okay. It is V1 square plus U square minus 2 UV1 cos alpha 1, right. Now, here we take out this V1 square, 1 plus U by V1 is rho. So, rho square minus 2 rho cos alpha 1, because rho is U by V1, peripheral velocity, and is the ratio of peripheral velocity and the absolute velocity of steam which is entering the turbine. So, delta H played is V1 square, and we will put the value here 1 minus phi times 1 plus rho square minus 2 rho cos alpha 1 divided by 2 efficiency of the nozzle. This is enthalpy drop in the blades, and same is the enthalpy drop in nozzles. We multiply this by 2, we will get the enthalpy drop in a stage, or if we remove 2 from here, we will get enthalpy drop in a stage. Except for the first stage, the gain in kinetic energy in each row of fixed and moving blade is V1 square minus phi V2 square by 2 is equal to V1 square minus phi VR1 square by 2, except for the first stage. So, delta H in a stage is twice of this, so it is V1 square 1 minus phi 1 plus rho square minus 2 rho cos alpha 1 divided by efficiency of the node. Okay. Now we want to find the Gauss stage efficiency. Now for Gauss stage efficiency, if you remember, efficiency for the Gauss stage, we need work and then change in energy, change in enthalpy. Now in order to find work, we need frill component of the velocity. Okay. So and delta H will take from here. Now will component VW of the velocity is, again we will refer this figure, we will refer this figure, this is will component VW, right. Now this is several ways we can express it, but we will take here as V1 cos alpha 1, this V1 cos alpha 1 minus U plus VR2 cos beta 2, right. Now V1 cos alpha 1 we will take as it is minus U plus VR2 can always be replaced by V1 in Parsons turbine. So it is V1, again beta 2 can be replaced by alpha 1. So VW is this much, or we can write 2 V1 cos alpha 1 minus U. Work is VW U. So we will multiply this by U and we will replace U is equal to rho V1. And when we replace this by V is equal to rho V1, we get V1 square 2 rho cos alpha 1 minus rho square. Now we will write the expression for Gauss stage efficiency. For Parsons turbine, the Gauss stage efficiency is going to be V1 square 2 rho cos, or we will write somewhere here, V1 square 2 rho cos alpha 1 minus rho square. So Gauss stage efficiency is W by delta H per unit kg. So per unit kg of mass flow rate. So this is divided by this will give us Gauss stage efficiency, right. And we can further simplify this by just putting Gauss stage efficiency is equal to efficiency of the nozzle. This will be cancelled out, right, and divided by 1 minus phi divided by 2 rho cos alpha 1 minus rho square plus phi. if you look at it here, 2 rho cos alpha 1 minus rho square, 2 rho cos alpha 1 minus rho square. So, if we take this minus inside, it will become 1 minus phi minus rho square plus 2 rho cos alpha 1. 1 minus phi we have taken as one expression. So, 1 minus phi. So, this is nothing but 1 minus phi plus phi 2 rho cos alpha 1 minus rho square, right. So, when this is replaced by this one, and when we divide numerator and denominator by 2 rho cos alpha 1 minus rho square, we get this expression. So, this is the final expression for Gauss stage efficiency. Now, in this expression, the Gauss stage efficiency is going to be the maximum in the case when this has maximum value, because efficiency of the nozzle is fixed, this is fixed, this is also fixed, only thing is remaining this. So, this has to be maximized, or Z is equal to 2 rho cos alpha 1 minus rho square. This has to be maximized with respect to rho. So, dz by d rho is equal to 2 cos alpha 1 minus 2 rho is equal to 0, or rho is equal to cos alpha 1. In impulse turbine, it was cos alpha 1 by 2, if you remember. Here it is cos alpha 1, okay, twice of that. So, now we can put rho is equal to cos alpha 1 here. Now, when we are putting rho is equal to cos alpha 1, efficiency Gauss stage is equal to efficiency of the nozzle 1 minus phi 2 cos alpha 1 square minus cos square alpha 1, right, plus phi, and this will give Gauss stage efficiency as efficiency of the nozzle cos square alpha 1, because this is going to be the cos square alpha 1 divided by 1 minus phi 1 minus cos square alpha 1, or cos square alpha 1 by 1 minus phi sin square alpha 1. This is the Gauss stage efficiency of impulse reaction turbine, Parsons type. It means if we know the blade inlet angle, we can find the Gauss stage, maximum Gauss stage efficiency, right. And but of course, we need to have the value of the efficiency of the nozzle or efficiency of the blade stage. After Gauss stage efficiency, we will derive blade efficiency or diagram efficiency, both are same, right. For blade efficiency, we need work and kinetic energy at inlet, right. So, first of all, we will calculate the work and then kinetic energy. So, in Parsons turbine, per kg of mass flow rate, work is like other turbines VWU, right, and W is equal to V1 square 2 rho cos alpha 1 minus rho square. This we have already done in previous case, right. So, we will not do it again. So, this is the work done. We do not have expression for kinetic energy. Now, the kinetic energy is the total energy, it is equal to half V1 square, the kinetic energy which is entering the blade, and change in kinetic energy VR2 square minus VR1 square by 2, right. So, W we are taking as it is V1 square 2 rho cos alpha 1 minus rho square, right, and total energy is this much. Now here you can see that VR2 is equal to V1. So we can always write half V1 square plus half V1 square minus VR1 square by 2. So they are going to be added. So it is V1 square minus VR1 square by 2. Now VR1, if you look at the velocity diagram, this is V1, VR1, U, then this is beta 1 and this is alpha 1. So VR1 in terms of V1 and U is going to be, this is VR1 square is equal to V1 square plus U square minus 2U V1 cos alpha 1, right. And same thing we will write here. So instead of VR1 square by 2, we will write half V1 square plus U square minus 2U V1 cos alpha 1. That is the total energy E, kinetic energy. Now after this, we will write the total energy as V1 square by 2, 1 minus rho square plus 2 rho cos alpha 1. So this is the total energy which is entering the blade. So blade efficiency is going to be a ratio of these two. And it is going to be equal to, when we take ratio of these two, this will be cancelled out and we will get 2 blade efficiency 2 rho cos alpha 1 minus rho square divided by 1 minus rho square plus 2 rho cos alpha 1, right. Now here also if you put rho is equal to cos alpha 1, so maximum blade efficiency max is going to be 2 times 2 cos square alpha 1 minus cos square alpha 1 divided by 1 minus cos square alpha 1 plus 2 cos square alpha 1, and this is going to be equal to 2 cos square alpha 1 divided by 1 plus cos square alpha 1. So this is the maximum efficiency of blade efficiency of Parsons turbine. Now here if we compare the efficiencies of impulse reaction and impulse turbine, then on the x axis if we take cos alpha 1, so the maximum efficiency for impulse turbine is like this. Here it is going to be the maximum cos alpha 1 by 2 and this is cos alpha 1. But here in this case reaction turbine, it is going to be like this. Here it is going to be maximum. This is for reaction turbine and this is for impulse turbine, right. Now after this we will do one worked example for Parsons turbine, not a Parsons turbine, this time we have taken, this is not a Parsons turbine, okay. So we will do one worked example on this reaction turbine, impulse reaction turbine. Steam flows, the problem statement is, steam flows into the nozzle of a turbine stage from the blades of the preceding stage. So it is not the first stage, right. So blades of the preceding stage with a velocity of 80 meters per second and issues from the nozzle with a velocity of 300 meters per second. So 300 meters per second is the absolute velocity which is leaving the stage and 80 meters per second is the absolute velocity with which the steam is entering the blade. And an angle is 20 degree to the wheel plane. Calculate the gross stage efficiency for the following data. Mean blade velocity is 160 meters per second. So, the U or the mean blade velocity is 160 meters per second. So, we will take them one by one. U is equal to 160 meters per second, right, and expansion efficiency for nozzle and blades 0.9, carryover factor that is phi, the nozzle is equal to 0.9, carryover factor is 0.75, degree of reaction is 0. This is not a Parsons turbine, because here the degree of reaction is 0.3. So, it is not, it is a reaction turbine, but it is not Parsons reaction turbine. Blade outlet angle, that is beta 2 is equal to 30 degree. As usual, we will draw first, we will draw the velocity diagram. This is V1, VR1, U, VR2, V2, beta 1, beta 2, alpha 1 and alpha 2, right. Now, delta H isentropic in nozzles is equal to V1 square minus phi V2 square by 2 into 1000. This is efficiency of the nozzle. Here V1 is with us. V1 is how much? 300. So, it is 300 square minus 0.75 into 80 square divided by 2, 0.9 into 1000, and that will give 47.3 kilojoules per kg. Because mass flow rate is not known, mass flow rate is not given here. So, we will take kilojoules per kg. This is enthalpy drop in nozzles. R is enthalpy drop in blades divided by enthalpy drop in nozzles plus enthalpy drop in blades, or enthalpy drops in blades is going to be equal to R by 1 minus R delta H nozzles. So, here we have enthalpy drops in the nozzle. So, this enthalpy drop can be taken here. R is given 0.3. So, R will take from here and we will get 0.3 divided by 1 minus 0.3 multiplied by 47.3, and that will give 20.3 kilojoules per kg. That is the enthalpy drop in the stage. So, here you can say, because the degree of reaction is less than 0.5, enthalpy drop in nozzles is more than the enthalpy drop in blades. In fact, it is more than 2 times. Enthalpy drop in nozzles in 2 times the enthalpy drop in the blades. So, once the enthalpy drop in the blades with us 20.3 kilojoules per kg. Once the enthalpy drop in the blades is with us, that is delta HB, that is equal to VR2 square minus phi VR1 square divided by 2 efficiency of the blades. Now, here again we will take VR2 square. VR2 square is, we will take from here itself, is equal to 2 delta HB plus 5 VR1 square. From this expression we can get the value of VR2. It is 2 times efficiency of the nozzles 0.9 delta HB we have calculated 20.3 plus phi is 0.75. What about VR1? VR1 is not known to us. VR1 is not known to us, but we have the value of VR1 square. We will write here VR1 square. But VR1 is not known to us. So, what we will do, we will take this triangle again. We have the value of u. We have the value of u with us. We have the value of V1 and we have the value of V1, we have the value of u. We have the value of alpha 1 also. This is 20 degree. We have the value of alpha 1 also at an angle 20 degree, right. So, we will take VR1 square is equal to V1 square plus u square minus 2u V1 cos alpha 1. Now, V1 is 300 plus u1 is 160 square minus 2 into 160 into 300 cos 20, and that is VR1 square, and then VR1 is 159.3 meters per second VR1. So, VR1 is 159.3 meters per second. Now, VR1 we can use here and we can find the value from here. We can take the value of VR1 and put this value here, and then we can get the value of VR2 as 326 meters per second. Sorry, you are 235, sorry, 235, it is 235 meters per second, 235 meters per second. Now, we have the value of VR2, we have the value of V1, and we have the blade outlet angle beta 2 value is also with us. Now, we can find the value of VW. Now, VW is whirl velocity. Whirl velocity is, we can take V1 cos alpha 1 minus u plus VR2 cos beta 2. This will give the whirl component. Now, V1 is 300 cos 20 minus u is 160 meters per second minus 160 plus VR2 is 235 cos beta 2. Now, the blade outlet angle is 30 degree, right. Now, this will give the value of whirl velocity as 326 meters per second, and this is VW 326 meters per second. Once we have the whirl velocity, we can find the work, multiply with this VW with u, we will get the work and enthalpy drop in the stage. So, Gauss stage efficiency is going to be equal to VW is VWu divided by delta H. So, 326 multiplied by 160 divided by delta H. Delta H is 20.3, this is delta H in blades, and delta H in nozzles is 47.3 multiplied by 1000, because this is in watts, right, sorry, this is in joules. So, and this is in kilojoules per kg. So, this gives the efficiency as 0.772, or the gross stage efficiency of the turbine is 77.2%, right. So, this is all for today. In the next class, We will start with the losses in steam turbines. Thank you very much.